All right, so I'm going to go through a little introduction for chapter 17. It's a lot of material in this chapter, so we're going to continue with probability, and we're going to encounter something called Bernoulli trials. So the basis for the probability models we will examine in this chapter is Bernoulli trials. Now, Bernoulli trials have three conditions. Number one is there are only two possible outcomes: a success and a failure. So it's like flipping a coin. You can either get, you can choose, okay, it's heads. Well, if you get heads, it's a success. If you don't, it's a failure. If you roll a dice, you want a 1. Well, if you get a 1, it's a success. If you get anything other than a 1, it's a failure. Okay, the probability of success P is constant. Okay, and that means that doesn't change. So when you flip a coin, the probability doesn't change. When you roll a dice, the probability doesn't change. When you draw a card, the probability does change. So if I was to say, well, what's the probability of drawing 2 cards from a deck of cards? The probability of the first ace, let's say, is 4 out of 52. The probability of the second ace is 3 out of 51. Probability changed. So that's not a Bernoulli trial. And lastly is the trials are independent. And that's like our card example we just talked about. Okay, when we flip a coin, each time we flip a coin, the fact that we flip the coin does not affect the next coin flip. When you draw a card, the fact that you took a card out of the deck does affect the next time you draw a card. Okay, so Bernoulli trials have 3 conditions. Okay. So the geometric model is basically we're looking for the first success. So for instance, if we flip a coin, on average, how many times will it take us to be successful? Well, the answer is 2. Okay, on average it'll take us 2 flips. That doesn't mean it will take us 2 flips, that's an average. It could take us 1 flip, it could take us 10 flips. Same thing with rolling a dice. If I want to roll a dice and get a 1, on average, how many times will it take us to be successful? Well, it would be 6 times. And that again is an average. It might take us once, it might take us twice, it might take us 13 times, but that 6 is an average. Geometric models are completely specified by one parameter P. The probability of success are denoted by the geom of P. Okay? So geometric models are about us finding our first success. So the geometric model continued. Geometric models, the P is the probability of success, Q is the probability of failure, and X is the number of trials until the first success. So I'll get into this formula, but this formula right here, this one, is what would be the probability that our first success occurs on the xth attempt. Okay, so for instance, what's the probability we get our first heads on our 4th attempt? Well, that means we would have, according to this formula, if we put 4 in q to the 4 minus 1 q to the 3rd, well, that means we would have 3 failures and 1 success. So we would do 0.5 to the 3rd times 0.5, which would be the probability of success. Now, if I wanted to know what's the probability of getting a 1 on a dice on the 4th attempt, that means I would have 3 failures and a success. So hence the probability of failure, 5/6 to the 3rd, 4 minus 1, times 1/6. Okay. This here, this mu equals 1 over P is the average. That's mu, the mean. The average time it takes to get a first success. Well, for instance, in our coin, if we do 1 divided by 1/2, well, 1 divided by 1/2 is 2. If we do our dice, 1 divided by 1/6, and that's going to come out to be 6. Okay, and then the standard deviation formula is over here. We're not going to use that too much. Okay, independence. One of the most important requirements for Bernoulli trials is that the trials are independent. When we don't have An infinite population of trials are not independent. But there is a rule that allows us to pretend we have independent trials. So for instance, if we're sampling people in the city of Norwalk, there's 75,000 people. But every time you sample one person, the population that's left, because you've sampled one person, that probability is now changed slightly. It's like drawing from a deck of cards, except now you have 75,000 cards. Well, you have a very large population, so really each person is not independent, because after every person you ask a question to, the rest of the population probability now changes ever so slightly. So you have what's called the 10% condition, and the 10% condition says if we're sampling without replacement, it's okay to sample as long as we sample less than 10% of the population. And the reason being that you're sampling without replacement. So if we're going to sample in Norwalk our 75,000 people, it's okay as long as we have a sample that's 7,500 or lower. We can still say that we meet the conditions of a Bernoulli trial. So that's if we're sampling without replacement. So we looked at a geometric model which tells us the probability of our first success. Now we're going to look at a binomial model. It tells us the probability for a random variable that counts the number of successes in a fixed number of Bernoulli trials. So for instance, a binomial model might be if we were flipping a coin. What's the probability if we flip a coin 5 times that we get 3 heads? The two parameters define the binomial model: n, so in our case 5, the number of trials; p, the probability of success. You know, this is binom n comma p. Okay, so this tells us we want to know the probability out of so many successes. Okay, so I'm going to go into this as we go into our notes, but what this is if I was to figure out, for instance, if I flip a coin 5 times and I want to see 3 successes out of those 5, what comes into the equation now is another variable, and that other variable is that order matters. So for instance, if I flip a coin 5 times, there's more than one way for me to get 3 heads. For instance, I could get heads, tails, heads, tails, heads. So I got 3 heads. I could get tails, heads, 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 tails. So there's a myriad of ways that can happen. Actually, there is a fixed number of ways, and this is a formula I will go into that we actually won't use, but it'll help to explain. So this is called this n choose k here. That's how we say that, n choose k. Tells us the number of combinations that are possible if we were to do something n times and we want k number of successes. Okay. And again, I'll go into that formula later, but just understand that when we're dealing with binomial situations can happen in more than one way. Order matters. Okay. So the binomial model, what happens is we have these 3 variables now. So the 3 variables that we are now dealing with are, here's n, the number of trials; x is the number of successes; and then p is the probability of success. And then from p, obviously, you would get q, which is the probability of failure. So for instance, here's basically what this model is saying. If I was to look at the probability of getting 3 heads out of 5, well, all this is saying is this would be 0.5 to the 3rd, and this would be 0.5 to the 5 minus 3, which is 2. So I would have, in essence, I would have 3 successes, and I would have 2 failures. Where did my thing? 2 failures right there. However, those 3 successes and 2 failures can happen more than one way, and that's what this whole deal right here is. Okay, so I got to figure out not only the number of successes and then the probability, so I do the probability to the number of successes and Q to the number of failures, but I then must figure out how many different ways that can happen. Okay. Alright, so here is the average number of successes that we would find, and I think we've gone into that already, but if I was to flip a coin 100 times, how many successes would you expect? Well, you would expect 50, and that's an average. It doesn't mean 50 will come up every time, but what did you do to get 50? Well, you did N, which is the 100 times you flipped the coin, and P is the probability of success, which is 1/2. 100 times a half. Okay. If I was to roll the dice 60 times, how many ones would you expect? Well, you'd expect on average 10. Well, what did you do? You did 60 times 1/6 and you got 10. Okay, and then this whole standard deviation deal I will go into as we go into our notes. But basically we use these two when we have a large number of trials. So we'll go into that in our notes. So we're going to be dealing with the normal model again, and again, to use a normal model we need a mean and we need a standard deviation, and we'll go into that and into the chapter. So when we're dealing with a large number of trials, so for instance, you know, we're flipping a coin 10,000 times, and we want to know what's the probability that we get 5,500 heads. Normal models sometimes, well, actually the normal model is an interval, so we would want to know what's the probability that we get between 5,000 and 5,500 heads if we were to flip a coin 10,000 times. We could figure that out using the normal model, as long as we know the mean and the standard deviation, which we'll know how to calculate. Okay. We can do this as long as our success failure condition holds, and that is NP must be at least 10 and NQ is at least 10. So if we're flipping a coin 10,000 times, 10,000 times 1/2 is 5,000. That's certainly more than 10. And the number of successes would be 10,000 times 1/2, which is at least 10 also, because that's also 5,000. So we really only use the normal model if we have a very large number of trials. Okay, so just be aware of that. Now the whole deal with using a normal model is the normal model is a continuous random variable. So we use that, you know, if we're looking at measurements, which we were talking about in a previous chapter. You know, whenever we're looking at the probability in between two intervals, we're including everything that's in between those two intervals. So that's a continuous variable, though when we're looking at probabilities, you know, if I'm looking at the probability between 5,000 and 5,500 heads being flipped, I could get 5,000, I could get 5,001, 5,002. Those are discrete random variables. Okay, I can't get 5,000 heads. I can't have fractions or decimals. So these, when we're talking about this, we're really talking about a discrete random variable, but a normal model is a continuous random variable. So we just have to be aware that we're using a continuous model to approximate a discrete situation. So that's basically what that comes to. Okay, so what can go wrong? Be sure we have Bernoulli trials. You need 2 outcomes per trial. So, you know, it has to be a success-failure situation. A constant probability of success. So if the probability, you know, if you were to do something, let's say you were to go and you know, take a test, and the probability of passing is 60% the first time and 80% the second time, well, that's not a Bernoulli trial, because probability changed. And independence. And if you don't have independence, then you need to follow the 10% condition. We'll go into geometric and binomial models, and when we use normal approximations, we will use those for large n values, you know, large samples. Okay, in order to use the normal model, we must have at least 10 successes and 10 failures in order to use that. So what have we learned? Bernoulli trials show up in a lot of places. Okay, they're in essence a probability, and depending on the random variable of interest, we might be dealing with a geometric model, which would be finding our first success, a binomial model, finding the number of successes out of a fixed number of trials, or a normal model, which it would be an approximation of a discrete random variable using a continuous situation. So what we have learned about geometric models when we're interested in the first success. Binomial models, like I said, when we're looking for a fixed number of successes out of an n number of trials, and the normal model, and the normal model must meet the success failure condition. Alright, so to start the chapter, we talked about this. Bernoulli trials. In order to be a Bernoulli trial, it has 3 conditions. You can now only have 2 outcomes, success and failure. And if you can't read my handwriting, that is my version of success. Success we denote as P, and failure we denote as Q, and Q is 1 minus P. Okay? So the probability of success which is P, is the same for every trial. Okay? And lastly is the trials are independent. And as we talked about in the introduction, if they're not independent, then they must meet the 10% condition. And the 10% condition says that we're allowed to sample without replacement as long as we sample less than 10% of the population. And that we know we're violating the independence assumption. However, it should not change the probability significantly enough that it will cause our sample to be to not be a good approximation of what we're looking for. Okay. So common examples include tossing a coin. Okay, that's a Bernoulli trial. Having a child. You have a 50-50 chance of having a boy or a girl. So however you view success. Okay, and each child is independent. Alright, and the probability of having a boy or a girl is still 50% no matter how many you have. And then rolling a dice. Okay, so if we want to get a number on a dice, there's a 1/6 chance. That probability does not change, and each roll of the dice is independent. Alright, so in problem 1, we have a situation where the probability of success of event A is 0.25. So that must mean in this situation P is 0.25 and Q is 0.75. So what is the probability that event A has its first successful attempt on the 3rd attempt? So this is the probability that our X, which is our first success, equals 3. Well, there's really only one way that can happen. I can fail, and I could succeed. Or the person can fail, and succeed. So these all have probabilities to them, so this is really failure squared times success. Well, failure is 0.75 squared times success. You can do that out. You get 0.140625. 0625. Okay. So what is the probability that they're successful? Now the first one was on by the 3rd attempt. So that must mean that probability X can equal 1, or X can equal 2, or X can equal 3. they can be successful on the first, second, or third attempt because it's by the third attempt. Well, the probability they're successful on their first attempt is 0.25. Or means add. The probability they're successful on their second attempt would mean they failed on the first attempt and then were successful. And that comes out to 0.1875. And or the third attempt we did up here, so that's 0.140625. So if we add these up, we get 0.578. And then how many attempts do you expect to try on average for this person to be successful? Well, the mean for our first success is 1 over p. So that's 1 over 0.25. Now remember, 0.25 is 1/4. So if the probability of success of something is 1/4, then on average we would expect four attempts to be successful. Now that doesn't mean that's what will happen. It's an average. If we were to do this time and time and time again, it would be an average of 4 times until we got our first success. Okay, and that's simply 1 divided by 0.25. You need to know this guy. This guy is not on your AP formula sheet. So you got to know that one. Alright, so you have an example here of Mr. Dustin's an 80% free throw shooter, or so he claims, and he is going to shoot 5 free throws. So we got to find each of the following. So the first thing we need to understand is if we give Mr. Dustin 5 free throws, there are 6 things that could happen. He can make 0, he can make 1, he can make 2, he can make 3, he can make 4, he can make 5. And each of these has a probability assigned to it. And those probabilities are not equal. Actually, this would be the highest probability because 80% of 5 is 4. So he's most likely to make 4. And he can do any one of these, so this or this or this, so we add those. And if we were to add those 6 probabilities together, they would add up to be 1, because those are the only 6 things that can happen. Those, by the way, are discrete probabilities. You can make 0 or 1, but you can't make a half a free throw. So we're going to go through all these. So how many different ways can he make 0 free throws? Well, that means he would have 5 failures. Well, the probability of success is 80%, so P is 0.8, so Q is 0.2. So this would be 0.2 to the 5th. Okay. So if we did that, and that's 3.2 e to the negative 4th on your calculator, so that's 0.00032. So it's highly unlikely that he would make none. Okay. Well, next he can make 1. Well, how many different ways can he make 1? Well, he can make the first and miss the next 4. He can miss the first, make the second, miss the next 3. He can miss the first 2, make the third, and miss the last 2. He could miss the first 3, make the 4th, and miss the 5th. Or he can miss the first 4 and make the last one. Now, this could happen, or this, or this, or this, or that. Now, the nice thing is, remember back to your algebra class, you learned something about the associative property. And what the associative property says for multiplication is, if you're multiplying things, it doesn't matter what order you multiply things in. So all I know is in every one of these I got to multiply 0.2 4 times, and I got to multiply 0.8 once. So it really doesn't matter. This is going to equal this, which is going to equal this, which is going to equal this, which is going to equal that. So I can just find it once and add it 5 times. So really what I'm going to do is I'm going to do 5 times 0.2 to the 4th times 0.8. And if I do that, I get 0.0064. More likely than that, but still less than 1%. Okay. Now we list all the ways he can make 2 free throws. So there's actually 10 ways this can happen. And the first way is he can make 2 and miss 3, and then he could make, miss, make, miss, miss, make, miss, miss, make, miss, make, miss 3 in a row, make the last one, miss the first one, make 2 in a row, miss the last 2, miss, make, miss, make, miss, miss, make, miss, miss, make, miss, miss, make, miss, 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 make, miss, make, and then the last way is he would miss the first 3 and make the last 2. So again, all of these have 0.8 times 0.8 times 0.2 times 0.2 times 0.2. So really we have 0.8 squared times 0.2 to the 3rd in all of them. And there are 2, 4, 6, 8, 10 ways. Don't forget this one right here. Okay, so there are 10 ways that that could happen. So we're going to do 10 times 0.8 raised to the 2nd times 0.2 raised to the 3rd. And that's 0.0512. And then we do all the ways he can make 3 free throws. So the first one he could do is make 3 in a row and miss the last 2. So let's see here. He could miss, miss, make, 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 miss, make 2 in a row, miss and then make again, miss, make 3 in a row and then miss, miss, make, miss, miss and then make the last one, make the first one, miss the next 2, make the last 2, make, miss, make, miss, make, make, miss, make, make, miss, make, make, miss, miss, make, and then make, make, miss, make, miss. Okay. So again, there are 10 ways here, and we would do 0.8 cubed times 0.2 to the 2nd. And if we do that, get 0.2048. So you can see our probabilities are coming up. Again, he's an 80% free throw shooter, so you can see we went from here to here to here to here. Now there's 5 ways, right? So he can make 4 and then miss the 5th one. He can make, miss, make. Then he can make, miss, make. Then he can make, miss, make the last 3, and then the last thing he can do is miss and then make the last 4. So all of these have 4 successes, so there's 1, 2, 3, 4, 5 ways that can happen. So that would be 0.8 to the 4th times 0.2. So 5 times 0.8 raised to the 4th times 0.2, and we get 0.4096. And then the last thing is he can make 5 free throws. So those would be all successes. There's only one way that can happen. That's 0.8 to the 5th. and that's 0.32768. So we have our 6 outcomes. Probability makes none. 1, 2, 3, 4, and 5. Okay? So if we knew this, actually we're only going to do A and B. We don't need this is A and B. If we wanted to make at least 2 out of 5, then what would the probability be? Well, at least 2 means 2 or more. So it would be the probability he made 2, 3, 4, or 5. Probability he made 2 is 0.0512. Probability he made 3 is 0.2048. Probability he made 3 is 0.4096, and the probability he made 5, so 2, 3, 4, 5 is 0.32768. If we add those up, we get 0.99328. And then the last one is, what's the probability he made no more than 2? Well, the probability he makes no more than 2 means he made 2 or less. So 0, 1, or 2. The probability he made 0 is 0.00032. Probability he made 1 is 0.0064. And the probability he made 2 is 0.0512. So we do 0.00032. 0.0064 and 0512, and that comes out to 0.05792. Alright, so here's the deal. So we get this problem here, and obviously every time we get one of these problems, we don't want to sit here and figure out, well, obviously if you have all failures or all successes, those are pretty simple. There's only one way that can happen. But when we get 1 success or 4 successes, there were 5 different ways that could happen, and every time we get a problem, we don't want to sit here and list out all the possibilities. So, in other words, where does this 5 come from? And where does this 10 come from? And where does this 10 come from? And this 5? And we all already know where the 1s come from for all successes and all failures. Okay, so I'm going to show you a few different ways to get there, and just for your background knowledge. Okay. So when we're given n number of trials and we want to find k number of successes, we write this as n choose k. This gives us the number of outcomes possible. Actually, when I write it, I'm going to write it as also as n choose k. So in other words, if I want to look at, I have 5 trials and I want to know the number of outcomes. If I have 3 successes, I could do it like this. That's acceptable. Or I could do it like this. 5 choose 3. Okay, either one is successful. Either one of those is acceptable. Okay, I do not put a fraction bar here. It's not a fraction. It's a notation. Okay, it's just saying 5 choose 3. Okay. So the first way we could do it is we can use what's called Pascal's triangle. Okay. So Pascal's triangle looks like this, and it's a pattern, keeps on building, and these ones keep going down the triangle on the sides, and then in the middle you keep adding these 2 numbers. So this is 4, 6, and then 4, and then 1, and then this would be 1, and this would be 5, and this would be 10, and this would be 10, and this would be 5, and this would be 1. Well, this is the row I want to look at. Okay, so what does this mean? Well, basically what this means is if you were to flip a coin or whatever you're going to do, this is the number of trials going down the side. So this row would be 0 trials, and this would be 1 trial. Well, if I do 1 trial of something, I can have 1 success or 1 failure. And then this would be 2 trials. Okay, so there's 1 way to get all successes. Okay, 2 ways for us to get 1 success. So think about if we were to flip a coin twice. Well, I could get let's say I'm looking for heads. There's only 1 way I could get all heads. But there's 2 ways I could get 1 head. I could get heads, tails, or tails, heads. And then there's only 1 way I could get all failures. That would be tails, tails. And then this would be 3, and this would be 4. And look at this. This is our 5 right here. Well, this is what we just looked at. So there's 1 way for Mr. Dustin to hit all of his free throws. There's 5 ways for him to hit. Let's start from left to right. There's 1 way for him to hit no free throws. That'd be all failures. There's 5 ways for him to get. So this is the probability of 0. Okay, so there's 1 way that can happen. This is 1. There's 5 ways he can get 1 success. There's 10 ways he could get 2 successes. There's 10 ways he could get 3 successes, and there's 5 ways he could get 4 successes, and there's only 1 way he can get 5 successes. So Pascal's triangle is 1 way to find a number of combinations. Okay. The second way is on your calculator. There's a button called NCR. So if you go there, first you got to turn it on. Let's try that again. Alright, and go to math probability, and not that. Alright, so let's go to see that NCR button. Okay, so here's how this works. So Mr. Dustin is going to shoot 5 times, and we want to know how many ways he could get 3 successes, and we already know that's 10. So the way you put that in a calculator is you do 5, and then you go math probability NCR 3. Okay, and then if you do that out, that should be 10. Okay. So how many ways can he make 5 out of 5? Well, it should come out to be 1. So I do 5 and probability NCR. So how many ways can he make 5 out of 5? There's 1. It would be all successes. So that's the NCR function. The NCR function on your calculator, and this is a capital C, small r. NCR function on your calculator, and that's math probability. Okay. And then there's this formula that we looked at in the beginning, and it's n choose k. And how do we get the number of successes? Well, we do n factorial, and then we do k factorial, which is the number of successes we're looking at, and then n minus k factorial. Okay, so if you remember what factorial means, 5 factorial means you do 5 times 4 times 3 times 2 times 1. So if I want to do 5 choose 3, I do 5 factorial, and let's see, yeah, there it is. If you go to the probability function, there's the factorial key. So 5 factorial is 120. So well, let's see, let's fill this in first. N is the number of trials, k is the number of successes. and let's see, n minus k, the number of successes, and let's see, n minus k. I think there's supposed to be another letter there. I think that's R. I think that some books have it as R. Don't worry about it. I'm just going to show you how it works, and just so you, for your own background knowledge. So let's do our 5 choose 3 again. Okay, so 5 choose 3 is what we have to do is we know 5 factorial. That's the number of trials. That's n factorial. 3 factorial over 5 minus 3 factorial. Okay. So we know that 5 factorial is 120. 3 factorial, 3 times 2 times 1 is 6. And 5 minus 3 is 2. 2 factorial, 2 times 1 is 2. So we get 120 divided by 12, and that's 10. And that's the same 10 that we got here, and that's the same 10 that we got there. So that's how you get. That's 3 different ways of finding the number of combinations. Okay. Okay, so when we're finding k successes out of n trials, this is called binomial probability. Okay. The key to this is that there is a fixed number of trials. So as opposed to a geometric situation where I say, well, what's the probability of the first success on the nth trial? In this case, I want to know, it's always out of something. So what's the probability that the person gets 3 out of 5, or at least 3 out of 5, or at least no more than 3 out of 5? There's always a fixed number of trials there. In a geometric situation, you're only looking for the first success. Alright, so let's go into the calculator now. The nice thing is we will never actually do all that with the either Pascal's triangle or the NCR function or that dreadful formula that I showed you. But again, having the understanding of where those come from is good background knowledge to have. So in order to do this on the AP exam, we would show that we have to show our work on the AP exam. So let's see, does that work over there? Put the light on. So for geometric probability, there are a couple of commands that exist, but I don't use them. I find them it's just easier to just figure it out using kind of intuition. You know, the number of failures is always one less than the first success you're looking for. So if I'm looking for my first success on the 10th attempt, that must mean I failed 9 times and had the success on the 10th time. So it's failure to the 9th time success. It's pretty simple. But this whole thing with binomial probability is another whole other thing. Okay. So if I'm looking binom PDF and it's exactly k successes out of n trials, then I go to this binom PDF thing. Okay. And if I go to second distribution and I go down to binom PDF, and let's say Mr. Dustin, 5 trials, and the probability of success for him is 0.8, and the x value is the number of successes. So let's say we want to know 4 successes. Okay, and then we go ahead and we knock that out. Remember that 0.4096 that we got? So look at that. Without doing all this, calculator just banged that out for us. So we didn't have to go and do all that. So binom CDF is the sum of 0 to k successes out of n trials. Your calculator uses x here, by the way. For whatever reason, I'm old school, I still use k, but this is actually x. Okay, so let's see. 0 to 2, right? Probability he makes, Mr. Dustin makes 2. So this would be a no more than. So we're going to go to binom CDF. And CDF, I always say, is cumulative, and PDF is precise. So precisely 3 out of 5. Cumulative is always 0 to a number. So 5 trials, 0.8, and the X value is 2. And we go ahead and we paste that, and we get that 0.05792. Yeah, look at that. No more than 2 out of 5. Well, what does no more than mean? It means the sum of 0 to 2. That's what binom CDF does for us. It sums from 0 to wherever we tell it to sum to. So that makes life a whole lot easier, though we do have to show the work, and I'll show you what we got to put down on the paper in a few minutes. Okay, so you got to know how to use these two. Okay, binom PDF. I always use the word P, precise. Precisely X out of N or K out of N. C is cumulative. And cumulative starts with 0 to whatever. Okay? That's how we're going to use our calculator going forward. Alright, so let's look at Mr. Dustin now with our calculator. Alright, so he makes 2 free throws. Now that's precisely. So, how many are we giving him? Well, we're giving him 5 again. Alright, so let's say we don't know. We know that 5 choose 2. Let's see, 5 choose 2. If he makes 2 free throws, we know there's 10 ways that can happen, right? We're not going to worry about that. So here's what we're going to put down in our paper. This is a binomial situation, so it can happen in more than one way. So I have to put either down 5 choose 2 or 5 choose 2, whichever way you want to put it. And he has 2 successes, so that's 0.8 squared. And if he's shooting 5 free throws, that must mean he had 3 failures. And that's 0.2 cubed. Okay, so we have this number of combinations. And this is the probability of each combination, each different one. Each different combination is going to have 2 successes and 3 failures. And at this point, we just go to our trusty calculator and we say, okay, calculator, second distribution, binom PDF, because it's precisely 2 out of 5. 5 trials, 0.8, 2 successes, bada bing, 0.0512. We're done. Okay, now, if you put down on your paper this, and you do not put the number of trials in front, and you put this down on your AP exam or my test, you're going to get a big X in it, because that doesn't equal 0.0512. Okay, this, you would have to multiply this by 10, because the 5 choose 10, 5 choose 2 is 10 different ways. So you can't just put that down. You gotta have the 5 choose 2. Now, you might be asking yourself, Mr. O'Neill, I have to evaluate 5 choose 2. No, you don't. That's the beauty on the AP exam, right? All you have to show is that there's that many combinations, even though you don't know how many those are. I don't know, let's say it was 10 choose 7. I don't know what 10 choose 7 is. I don't really care to find out. But I just have to show that there's that many combinations on my paper. Okay, now if you want to figure it out, go to use your NCR button, okay, and you can figure it out. Okay, so he makes 4 free throws. So we already know if he makes 4 out of 5, there's 5 ways that can happen. So we're going to do 5 choose 4. And then he had 4 successes and 1 failure. Okay, so I go to Mr. Calculator. I say, Mr. Calculator, this is precisely 4 out of 5. And the calculator says, okay, 0.4096. Okay. And this should probably, I always, this should be in parentheses, or you could do this. This is fine too. Either one is okay. Okay, he makes no more than 2 free throws. So no more than means he makes 2 or less. Well, what's the least number he can make? Well, he can make none. So you can put down 5 choose 0, though you don't have to, because 5 choose 0, any number over 0, 5 choose 0, 10 choose 0, 100 choose 0, there's only one way that can happen. That means that they were all failures. Well, if they're all failures, there are no successes. There's only one way that can happen. So you don't have to put it. Okay, we'll put it just we don't have to put that because there's only one way that can happen, and that means that he missed them all. So that's point. Again, if you want to put 0.8 to the 0, you can, but 0.8 to the 0 is 1. Any number to the 0 power is 1. You don't have to put that. And we got to go 0 plus 5 choose 1, 0.8 times 0.2 to the 4th, and then we got to do 5 choose 2. No more than 2. 0 plus 1 plus 2. And this would be 0.8 squared times 0.2 cubed. Now, when I would write this on my paper, here's how I would write this. I would say 0.2 to the 5th, I wouldn't even put that down, plus dot dot dot, add up to 5 choose 2, 0.8 squared, and 0.2 cubed. Okay, you can use the dot dot dot. All it's saying is we're going to add up everything in between those. So if I was saying, oh, you know, he's shooting 10 free throws, what's the probability he makes no more than 7? Well, no more than 7 means you've got to add 0, 1, 2, 3, 4, 5, 6, 7. I don't want to write all this stuff down 8 times. So I'm just going to write 0 to 7, okay? And then this is simply binom CDF. Okay? So we go to second distribution, and we go to binom CDF. And this would be 5.82, and knock that out, 0.05792. Which, by the way, we got here. That's the same thing we got here when we added 0, 1, and 2. Okay. Okay. And now at least 2. All right. So here's where it's going to get a little bit tricky. You can add at least 2 means 2 plus 3 plus 4 plus 5. Now, you can't use binom CDF. Well, why not? Well, because binom CDF adds from 0, the probability of 0 to the probability of something else, whatever our x value is. Well, 2 to 5 is not 0 to some number. It's from 2 to 5. Now, stay with me for a minute. There are 6 different things that can happen here, correct? He can make 0, he can make 1, he can make 2, he can make 3, he can make 4, and he can make 5. And if I add all 6 of those different outcomes together, I get 1. Those are the only 6 things that can happen, and though they all have different probabilities, which we found out over here, remember, here's the probability of 0, 1, 2, 2, 3, 4, and then 5. Okay? So, at least 2 means I want to know this right here, from 2 to 5. Now remember when we did at least 1? At least 1 went from 1 to 5. Well, what did we do? We did 1 minus the probability of none. Now if I'm looking for at least 2, I have to do, I could either find these 4 probabilities separately and add them together, which is too much work for me, or I could find out what this thing equals here and subtract it from 1. Okay, just bring it over to the other side and subtract it from 1, because all I want is what's in this box here. I don't want anything else. Well, how do I find that? I find that using binom CDF. I say, oh, okay, I want to know what's the probability of 0 plus 1. Well, I go to my calculator and I say, okay, calculator, binom CDF, okay, 5.8, I'm sorry, add from 0 to 1 for me, okay, and look, I get 0.00672. So this is 0.00672. So if I do 1 minus that, which all I do is I say, I would do this all in one step, by the way. I would just do 1 minus binom CDF. And then I would do this, and I would just have the calculator knock it out. 0.99328. Okay. Well, when we got these here, when we did these all separately, remember we added 2, 3, 4, and 5 when we got 0.99328. So whenever we're doing an at least problem, we can stay consistent, just like we did from the previous chapter. We said at least 1 was always 1 minus the probability of none. Well, at least is always going to be 1 minus the probability of 1 less than the one that we're looking for. So if I'm looking for at least 1, I subtract 1 minus the probability of 0. If I'm looking for the probability of at least 2, I do 1 minus the probability of the sum up to 1. And that's always done using binom CDF. Okay? So I know that's going to be, that's always a like, holy cow, what just happened kind of moment, but that's something that we're going to continue to build upon as we go into class, and we do these type of problems. So here's the deal. When you're doing precisely a number out of a total, it's binom PDF. So this is PDF, this is PDF. When you're doing no more than, which means you're summing from 0 to a number, this is CDF. When you're doing at least, this is 1 minus CDF. Unless it's at least 1, and then you could just do PDF. But if you did CDF, it wouldn't be wrong. If you put 0 in the CDF, it would be fine. Okay, you could always. My point is, you can always use binom CDF to do an at least problem. Okay, to make it just consistent all the time. Okay. Okay. So again, the stuff that has to go on the paper on this problem, I would do at least 2. I would do 5, choose 2, 0.8 squared, 0.2 cubed, plus dot dot dot. And then I would do 5, choose 5, which I wouldn't put on my paper because I know that's 1, and I would do 0.8 to the 5th. I would put a plus sign there. So what I'm showing on my paper is I'm adding from 2, 3, 4, all the way up to 5, and then I'm completing my addition. And then I put the equal sign, and this part you do not have to put this stuff, this calculator stuff, on your paper. The calculator stuff is just what you use to evaluate the probability. Okay, so let's look at a binomial distribution now. And basically what we're looking at here is if we roll a dice, the probability that any number comes up, let's say it's a 3, would be 1/6. And I'm going to roll it 6 times. Well, if I roll a dice 6 times and I want to know how many 3s will tend to come up, we see here that the probability that no 3s would come up would be 24%, which is a possibility. We'd expect 1 3 to come up most of the time if we were to roll a dice 6 times, and that's 40%. And 2 3s would be 20%, and then 3 3s would be 4%, and then 4 3s is less than 1%, and then 5 3s you could see is smaller, and then 6 is even smaller. But you see the shape of the distribution? You know, the shape of the distribution is, you know, skewed right. Okay, so we have a distribution that's skewed right, but the other half of the distribution is somewhere over here. Okay, it's over in this area over here. Okay, but that part of the distribution doesn't exist because I can't roll less than 0 threes. It's impossible. You can't roll -1 3, so that part of the distribution does not exist. Okay. Now, let's say that we roll it 60 times. Okay. And okay. So now, what we have is a distribution, and what occurs most frequently in the middle here is 10. Well, if I was to roll a dice 60 times, I'd expect 10 threes to come up most of the time. But then you have 9, and then 8, and then 7, and then 6, 5, 4, 3, then 2, then 1, then none. Okay? And then the other side of the distribution on the other side of 10 goes this way. Okay? Now, this distribution now is more symmetric. Okay, so we have a distribution that's, you could say it's slightly skewed. It's not perfectly symmetric, but it is a lot more symmetric than when we only roll it 6 times. Okay, so now let's roll it 600 times. Actually, let's not roll it 600 times. Let's roll it 300 times. Okay, so we roll it 300 times, and you can see that the one that's going to occur the most frequently here in the middle is 50. 50 would come up 6%, and then 49, 48, 47, it goes down from there, and then 51, 52, 53. And if I was to approximate this with a normal distribution, look at that. That comes out to be pretty unimodal and symmetric. Okay, so the point is, when we have very small distributions like 6, we wind up with a skewed distribution because the left side doesn't exist. Okay, but who cares? I mean, if we're rolling a dice 6 times and we want to find probability, I don't want to use a normal model. Okay, and if we have something like 60, it becomes more symmetric, though this is slightly skewed right still. Okay, and then when we have very large n sizes, we get a distribution that is pretty much unimodal and symmetric, and that allows us to use a normal model. Okay, so we'll just keep this in mind as we're moving forward into this next section on using normal models to do binomial probability. Alright, so let's take a look now. Suppose we had a problem where we're going to roll a dice 10,000 times and we want to find at least 1,006. This would take some work. In fact, it would take around 9,000 calculations. Because we'd have to add from 1,000, or actually 9,001 calculations, because we'd have to add the probability of getting 1,000 to the probability of getting all the way up to getting 10,000. So we don't want to do that, so we're going to use a normal model. Okay. We need the mean and the standard deviation. We already know how to calculate the mean because this is called the expected value. Or E of X. So suppose we have this deal right here. So the standard deviation is another story. So let's look at an example. The probability of getting a 1 is P, and the probability of getting 0 is Q. So the expected value here would be 1 times P is P, and 0 times Q is 0. So the expected value is P plus 0, which is P. Now our variance formula says we take each outcome, subtract it from the mean, square it, and multiply it times the probability. So to do the variance, we would do, our first outcome is 1 minus P squared times the probability, which is P, plus
0 minus q, I'm sorry, 0 minus p, p is the mean, squared times q. Well, what's 1 minus p? Well, 1 minus p is the probability of failure. That's really q. So this is really here q squared p. 0 minus p is negative p squared is p squared, and this is plus p squared q. Now I factor out a pq, and I get pq, and then q plus p. Well, we know that q is 0, and the p is 1. So this is really 0 plus 1. So it's really pq times 1, which is pq. So the variance for one trial is pq. What happens if we have many trials? Remember, trials are independent. So how would we? What would we do if we have independent trials? Well, to get the new mean, we simply multiply n times p, because our mean is p. So our mean is np. Okay. So if I'm rolling a dice 6,000 times, how many times do I expect a 3 to come up? Well, n is 6,000, p is 1/6. I expect the 3 to come up 1,000 times. That's what the mean would be. Okay. To get the new standard deviation, what do? We add the variances. So we wind up with our new. What we would do is we would add PQ plus PQ plus PQ plus PQ. How many times would we add PQ? N times. Well, if I add PQ twice, I could just put 2 PQ, right? If I was to add PQ 10 times, I would put 10 PQ. Well, we don't know if it's 2 or 10, but we know it's N, so it's NPQ, whatever that N is. However many times you're going to add it. If you're going to add it 100, it's 100 PQ. So what's the standard deviation? Well, the standard deviation is the square root of the variance. This is the square root of NPQ. So we wind up with a normal model with a mean of NP and a standard deviation of the square root of NPQ. Normal model, NP, square root of NPQ. By the way, these are both on your AP formula sheet. You don't have to memorize those. And by the way, the derivation that I just did, we just came to these. I'm not going to ask you to do the derivation. So that's always every year I get asked, do we got to do that? No, you don't. We just derived something, and we got the tools that we need, and the tools are we got the mean and the standard deviation. However, there's a problem. If we roll a dice 5 times and see the number of times a 6 comes up, our distribution would look like this. So what happens is it kind of cut off the distribution. The other half of the distribution is over here. But the problem is this is 0, and this is 1, and this is 2, and this is 3, and this is 4, and you can't get a negative outcome. You can't have a 6 come up negative 1 time, so the problem is we're skewed right. So the problem is this thing is skewed right. We like our distribution to be roughly symmetric. To use a normal model. Who cares? Because with 5 trials, we would use norm PDF. Binom PDF and binom CDF. We don't have to use a normal model to do something that simple. So it's a moot point. Okay. However, if we were to roll the dice 20 times, the distribution looks like this. Okay, much better, not perfect, but roughly symmetric. Do you see where it gets cut off a little bit over here? See how this, if this is the mean, this side's over here, this side gets cut off a little bit. There should be a little bit more over here. Okay, so this is still slightly skewed right, but not as bad. So where would this be centered at? Well, this would be centered at 20 times 1/6, and that comes out to be 3.333. So it's really centered. We can't have 3.333, so it's really, well, that would be the mean. Okay, so our mean here would be 3.3 repeating. Lower tail got cut off because we could not have less than 0 sixes. Now, you might be saying, Mr. O'Neill, hold on here. This is discrete probability. You can't have 3.336s come up. That's a mean. It's an average. Okay. So with 20 rolls, you could use a normal model, but probably wouldn't. Again, it would be easier to calculate. So when do we have enough trials to use a normal model? Okay. So here's our normal model, and here's our mean. And here's our mean plus 1 standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations, mean minus 1 standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. So, in order to use a normal model, the mean must be at least 3 standard deviations from 0. So this mu minus 3 standard deviations must be greater than or at least 0. So if I add 3 standard deviations to both sides, I could just rewrite this as mu is greater than 3 standard deviations. Substitute NP for mu and the square root of NPQ for sigma. So we have NP is greater than 3 square roots of NPQ. Well, we would want to get rid of that square, that deal right there. So if we square both sides, we would get n squared p squared. 3 squared is 9, and then when we square the square root of NPQ, we get NPQ. So I'm going to divide by NP here. And what do I get? I get on the left side NP, and on the right side I get 9Q. Since Q is Q is the probability of failure, well, the biggest that Q could be is 100%. So that must mean that NP, if I do 9 times 1, NP must be at least 9. So we will round to 10, so we're going to make NP be at least 10 instead of 9. Easier. So this kind of works both ways, and we're going to make NP be at least 10, and we're going to also make NQ be at least 10. We will only use normal models when we have a large number of trials. When we do, we must test this condition. This is called the success failure condition. Okay. So for instance, if we're doing the dice and we have n is 200 and p is 1/6, that means the q is 5/6. So actually, let's make this 300. Well, what's 300 times 1/6? So NP equals 300 times 1/6, and that's 50. So NP is at least 10. That's at least 10. NQ is 300 times 5/6, and that's 250. And 250 is at least 10 also. So this meets this condition right there. So
as long as our number of expected successes and number of successful failures is at least 10, we can use a normal model to approximate binomial probability. Okay. So back to our example of rolling a dice. I'm going to make this a nicer number for us. Let's see. Let's make this 9,000. We're going to make it 9,000 times. So our probability of success here is 1/6, and this is probability of failure is 5/6. So if I do 9,000 times 1/6, that's going to come out to be 1,500, I think. Yeah, it's going to be 1,500, and that's at least 10. And then 9,000 times 5/6 is 7,500, and that's at least 10. So we could use a normal model. It meets both conditions. When you do this on any kind of AP situation, you must explicitly show that this success-failure condition is met. Okay? You cannot just put, oh yeah, success, failure, yep, check mark. No, you got to show the calculation. So our mean here is going to be 9,000 times 1/6 is going to be 1,500, and then the standard deviation is the square root of n p q. Okay, so I'll put that in the old calculator, and let's do the square root of 9,000, 1/6, 5/6, like that. So the standard deviation, I'm just going to say it's 35.4-ish. It's approximately 35.4. Okay, so in this case, we want to know what the, let's see, we would get two z-scores, one for 1,600, so we would do 1,600 minus 1,500 over 35.4, and we would do 1,700 minus 1,500 over 35.4. So let's see what the z-scores come out. 1,600 minus 1,500, and that's 2.82. And then we'll just do 1,700 here, and that's going to come out to 5.65. So what does this look like? Well, this looks like if this is our mean is 1,500, 1,600, and 1,700 are over here somewhere. Okay. And then we go to the normal model. Remember norm CDF, and our lower bound is going to be 1,600. Our upper bound is going to be 1,700. Our mu is 1,500. Our standard deviation is 35.4, and the probability of that is 0.002. So it's under 1% with 0.0024. Okay. Keep in mind when calculating a probability with a normal model, it's an approximation. Okay, this is that whole thing about remember, we're approximating a discrete probability using a continuous model. So this is going to be an approximation. It's not going to come out exactly as if we were to do all the calculations. So just keep that in mind as we go forward.